Hey all, welcome to this video. Today we're talking about frequency response analysis, and I just want to dive into that topic because we got that request on some of the videos, the later videos. And just to start things off, I will try to cover direct frequency response analysis in this video, and we will do that by going through a tutorial and just wander around the topic, explore it a little bit. So stay tuned and let's jump into it. So I have prepared the OS tutorial. So it's again a OptiStruct tutorial, which is number 1300, and this is called the direct frequency response analysis of a flat plate. I already loaded in the model, and you can see here you have a shell element structure. And yeah, we will work with this shell element structure. So just that you know how I will go about things, I will just work here in the environment, and I will have my tutorial notes down here, so I will follow them. I will also post the link or the name of the tutorial also in here, and the video description, of course, because then you can also just go to the page and just follow it if you want to. So what we have done here is we have loaded the model here as a .fem file, and that's about it. So the first thing we do after having imported this model is we will create some SBCs. And just that you know what we're dealing here with, I will just simply show you what that actually is. So direct frequency response analysis. So just a little bit of Googling got me to this link, and I find this explanation pretty good here. So you have, for frequency response analysis, you have more or less two ways to go. One is the direct frequency response analysis, and the other one is the modal frequency response analysis. And they're all concerned with calculating the behavior of a structure under a frequency-dependent oscillating load. Oscillating load? Yeah. So you have an steady state, so it does not change, but you have a steady state oscillating excitation on the model. So you could just think of it as you have a ruler, and you put that ruler on the desk, so you have a free end, and then you just excite on the end in a controlled way, like up and down, up and down, up and down. As another free one, which just pull it down and let it go, because then the amplitude will drop, and this will be a different thing. But just if you have a 1 point, and you will excite that in a defined manner, you could say. So, all right, you see here direct frequency response. So this kind of analysis is highly efficient if you compared to the other one, if you have a lot of modal frequencies, a lot of modal modes you would have to extract. And so for direct frequency response analysis, you compute the structural response at discrete excitation frequencies by solving a set of coupled matrix equations using complex algebra. The direct method may be more efficient for models where high frequency excitation required extraction of a large number of modes. So it will be used if you have a lot of modes, and yeah, you really don't want to extract them all, but you rather want to compute that at different times and just see what happens there. So you could read about this. I just quickly glanced through it. So you have your just your standard motion equation, and you have a oscillating load, and then you define this oscillating function and set it in, build a derivative, and go on and solve it then for eigenvalues, I think. Yeah. So so there's a danger zone here for me, because I'm not the expert when it comes to frequency analysis. I understand the basic way of how to solve that, but I would have to just go a little bit more into that topic to explain it further. So, but I think it will be enough to just cover the reason why this frequency response analysis is carried out. And yeah, let's start with applying it here. All right. So we create first a load collector, and this load collector we call SPCs. And yeah, this is about it. color can stay the same. Then we do another one, which is called unit load. And what this is all about, we will see in a minute. Unit load. So we have two load collectors. I just opened the load collector browser with a double click, and you see the unit load collector is now the current one, which is not really the good thing, because we want to first create the SPCs. And yeah, just right click and make current to just use that here. Now, the tutorial will tell you that you would want to just display the nodes. And this was done in the panels, and the panel was called numbers. But yeah, this is not there anymore. But instead, what you can do is you have your selector here, and you just press N to go to nodes, and then you select all the nodes, and then you click right here, and then you just say more display IDs, or just press the letter Q. So this works. Now you have the node IDs, because that's important, as the tutorial will require you to just see which nodes you would like to constrain here, right? So that's the reason. Now, I will just orientate my model that I have the right nodes at the right side, which is the left side. And we'll go on to generate the boundary conditions. And this is done in analysis. Where is it? Here. Analyze, and then go to the boundary conditions. Not this little icon, here, this one. And whoops, here. Then you get this multi-menu, which you can choose between constraints, inertial relief, and MPC. So we just click on constraints, and now we are in the usual constraints panel. And I'm blocking things. I'm sorry about that. So I will have to move out of the way at some point. Now, what we want to do is we want to select all those nodes here. So we could just orientate it like this and just draw a rectangular, which with the letter, I think there's no letter required. Is there? No. So there was just some misbehaving function here. Now, just selecting those nodes. By the way, you can change this, the sphere or the boundaries of your selection box by just right clicking, and you have here this normal rectangle, you have a circle, and so you can select things differently, right? So you could select it with a circle and stuff. All right, but back to it. Let's change back to rectangular. Now we have all nodes selected here, right? You can see that with the orange dots. And now we just want to constrain all degrees of freedom here, I think. But not all, but 1, 2, 3, 4, 5, and the 6. That's really hard to say. I cannot do it. Sorry. All right. So the degree of freedom, this is the rotational degree of freedom in the Z direction, right? So you can see here the Z direction, which is this one, and we let rotation on this on these nodes. We will let that free. So this is just how it's set up. All other constraints are set to be constrained. And by the way, it's always nice to remember. You can see the zeros here. Those mean you would not want any translation in this particular degree of freedom. So just checking the boxes here won't do it. You also have to check that there's a 0 here, because if not, could be something which you don't want to do. Now click on create, and now you can see you have created those loads, which are constraints, but from a type they are loads. And now going back to the load collector browser, I think that's about it for here. And what we want to do now is to create the oscillating function, right? So we have now created the constraints where we hold this plate fixed, right? So we hold that in place. And then on the other side, we want to have a oscillating function which excites the plane or the plate here up and down, for example, at some point, right? So this is what we're doing next. Now, thing is, you have to go to create this unit load. First go into unit load and make that current, right? So you have the load collector unit load as the current load collector. And then you go into SPCs once again. Sorry, it's not a load. It's a load, but it's not really a load. Here you have another time you go onto the constraints. I could have used the same thing. But in this case, you would want to change your load type from SPC to D area. Right, is that D area? So, and just to show you what this is, I have put up here the help page. So this constraint here defines area factors for dynamic loads. D area is used in conjunction with, and you will see about this in a second, R loads and T loads. So R and T, those are either frequency dependent loads or time dependent loads. So let's just see what you're doing here. So this is a time or frequency dependent load, and we will use that here as a constraint. So what do we want here? We want this excitation to be in the degree of freedom 3, I think. Let me see. Yeah. So we uncheck everything here but the degree of freedom 3. And we will enter a 20 here. And as you see it here, that's where I have entered the 20. At the degree of freedom 3. Maybe that is better. So you can see degree of freedom 3, 20. That means 20 will be the amplitude. And we will discuss that later, but just bear in mind, this is the amplitude of the function we will later generate. So I will select the node number 19. So I haven't properly aligned it. So it's like this in the tutorial and click on create. So I have now this yellow constraint, which is a D area and is in the load collector unit load. All right, having done that. Now we can now create all the necessary stuff around this, because this is just putting the nodes and the constraints together, but we did not generate anything about the frequencies at all. So we will do that now. First of all, you will need a frequency range table. And this is just a table D1, which is more or less the simplest table which you can get. And just for your interest, I just also have put the help page here, so you can just see here. So table D1 defines a tabular function for use in generating frequency dependent and you could also say or time dependent dynamic loads. So you can do both here, right? And yeah, you have some pretty good comments here, because you can also see that you can interpolate linearly and also with logarithmic functions, and you have some things about discontinuities. This is allowed. It's not allowed to have a discontinuity here, but this will not really make a change here because our function will be pretty straightforward, which you will see in a minute. Now I will create a curve here. So right click, create and curve. This will pop up this huge curve window. Now you have this curve already here, which is the curve you just created. You can rename it to table D1 as the tutorial tells you to. And here it becomes tricky, I think, because it's not something you do here, but you have to push this thing here at the bottom up, and then you have your editor. So, and the editor, I'm sorry about that. And the editor here tells you to enter the values 0, 1. So you start with 1. And then you have to be in here and press tab. This will give you access to the other values. Now you put in 1000 and you put in 1 as well. So what does that mean? This provides a frequency range from 0 to 1000 with a constant of 1 over this range. So this is exactly what it's doing, right? So from 0, which is here, to 1000, which is here, it's all constant, like a straight line. Now, how this table D will come into play, we'll see in a minute, but you can see here the table D is represented under curves. And, I just almost forgot. It is not a table D, but we want it to be a table D. And you can see here the x-axis and y-axis interpolation function is set to be linear, which is exactly what we want to do. Not that it doesn't even matter because it's just a constant one. So, but yeah, forget about it. Now, go back to, we can close that. You see that it disappeared. The curve is not there anymore because we changed it to be a table D1, another table DMP1. So you will find it under curves, and then there's table D1. All right. Now comes the frequency-dependent dynamic load, which is a load step input, I think. It's not a load collector. It used to be, I think. This is the R load. Bear with me a little bit. So what we now want to do is we want to just create the dynamic load. And this you could do frequency dependent. So you remember hopefully that I told you about that the direct frequency response analysis wants to calculate at discrete frequencies. This is exactly how you set it up. So you could have R load 1 and 2, and I forgot already what the difference was. But the R load 2, let's go to the help again. The R load 2 defines frequency dynamic load of the form blah 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 for the use in frequency response analysis. You can see here the amplitude, and this is the oscillating function with the phase and all. And so R load 2 is given when you have this in magnitude phase number format, which is what we want in the tutorial. There's also R load 1. You could also check here, by the way. That's pretty a good help location to be in here. So this is the reference guide and then the bulk data section. So every keyword you can find there. So it's pretty neat. So going back down here. So just as you see, R load 1 would be something which is in a different format, I think. Oh, this was P load. R load 1, here it is. So R load is a frequency dependent dynamic input in real imaginary number format. So it's just a different formulation, but it's more or less a frequency dependent load. And we just happen to use R load 2 for our load here. So how we go about this? So we have the name, first of all. Let's stay the same as the tutorial. R load 1, 2, 2. R load 2. And this is dynamic load frequency dependent. That's right. And then type should be R load 2. Then excited should be a load collector. So this is the constraint you want to excite with this function. It's gotta be exciting. Sorry, that joke was bad. So unit load. All right, we press OK. We have selected this constraint to be excited with whatever we set up next. Now the TB and TP option, those two are important now. I think it is the TB, but I should know. So TP is, well, I'll have to look it up. Sorry. I think it's TB. So tutorial says I should place it under TB. Right, so I'll show it to you again. So this is where it gets a little bit complicated. So you have TB and TP. What does those values stand for? We know now we want to set it as TB here. But TB in R load 2 refers to identification number of the curve that gives the B, which is dependent on F. So this real value is used for BF for all frequencies. So we give that function from 0 to 1000, which with the constant 1 to be the B function here, right? So you have this one. So there's no multiplier in here. So the real value will be always 1. And the phase, yeah, so this is not concerned with the phase here. It's just the real value here. All right, that said, let's go back to here and just place the curve in here. So reference the table D, so this is done. And then we for sure have to set some options for how many frequencies. No, this is another thing, sorry. I think that's it, what we have to do for the RLOAD too. So what do we have here? We have the connection to the constraint, which we want to excite. And we also have the connection to the table D, which is our real value. And what is this TV option? Okay, this should not be a thing. All right, table D, set. Let's close that, so we have that. Now and I have to apologize. This was not the part where we set our discrete frequencies we want to calculate. This is the next step. So we create now a load collector, which is called, what is it called? Frequency 1. And has the card image frequency I. So this lets you add a number of different ways of how you define your number and properties of your frequencies. So let's go with frequency 1. So F1 should be the starting frequency, which is in this case 20 Hertz. I think it's Hertz, hope so. The delta frequency would be 20, and the number of deltas you would apply would be 49. Right, 49, sorry. Okay, so this is done here, and I think that's about it for the frequency load collector. And now we put it all together in a load step. So yeah, let's go about this. Load step. Can I do it with the panels? I think so, right? There should be here a load step. Is there a load step? Load, no. Sorry, I cannot find it. Still getting used to the ribbon menu, to be honest. But right click here, create and load step should do the trick. So load step. Now we want to have a, is it called frequency response direct? Yeah, this should be it. So let's create a reference to the SPC load collector. This is obvious, right? So this is, we'll get the SPC constraints here. Then the dynamic load should be also obvious. That's the R load. Yeah, because the R load itself references then the table D1 and also the constraint, which I was thinking about at first. Okay, R load. And then the frequency card should be also set, which is then, of course, the frequency 1 load collector. I think that's about it. Yeah. Okay, just one more time. You have the SPCs, which hold your structure in place. So those are fixed constraints. Then you have your another constraint, which is of the D area type. And this D area is referenced by a R load collector, or load step input, I should say. This R load step input references then also a table D1, which is the real part of the equation. The amplitude is the A part of the equation you get from here, so from the constraint itself. Then you have your R load defined. And for the frequency you want to calculate, you would have a frequency load collector as well, which you're referencing in the load step. So this would be all up to here. Now we also want to get some user-defined output. And so this will be a little bit more in-depth dive of the direct frequency analysis. So bear with me a moment. So we create a set. So sorry, you cannot see that. Right click and set here. And then we have, sorry, I will move myself up again. We have a, yeah, this is kind of funny here. So the tutorial calls you to set it to none, right? So, but you would want elements. I was just thinking, wait, I want nodes rather than elements. Tutorial says nodes, here's elements. And I got that trick, so if you change it to ordered and back to non-ordered, you get your nodes. I'm not sure if there's a smarter and more simple way to go there, but yeah, that worked. So we select the nodes, this one, and this one, I think. Let's see again if that's right. 15, 17, and 19. Yeah, seems about right. Apply, set one is okay. Close that. And now we go into the output requests. So you have your control cards, which should be somewhere here. Global output. Oh, wow. We can directly go to global output requests. Oh, that's good. But we will set up different cards as well, so we could also go for the control cards. But yeah, let's do it this way. And so for control global output request, we would want to have displacement. And the form should be, I think, real. Let me see. No, form should be phase. By the way, this is so much easier to edit here as in the controller cards menu. I will show that to you in a minute. But yeah, you maybe know. Okay, so we have displacement set, the form is set to phase, and we want to have under option, we just want to have it for one set. So set ID, and we just define the set ID. Didn't I create a set? Now it gets a little bit complicated here. Sets, collectors. Set 1. Card image none, non-ordered, 3 nodes. That's a bit strange. Why does that not work? Let's just go with 1. Does this work? No. Why does this not work? Okay. Oh, get an error. Getting slightly worried. But okay, let's go back. Let's delete. No, the set is okay, I think. Set is okay. Let's go the old way. This is the way. Go to control cards. Go to global output request, which is here. We have displacement already set, and now you see what I mean. So if you don't know about the slider and you just press this one, or I think, yeah. Somehow it works here. Oh, wrong entity. Select in ID group sets ID pool. I have no idea why this is the thing. Something is wrong here. Okay, now let's recreate the set. I'm not sure why it did not work, but let's delete the set. Let's create the set. Set 1. Now we'll just be sure that I am 100% safe about this. So we should go with a name, ID. All right, defined is also good. Card image should be none. Set type should be non-ordered. That's also correct. For entity IDs, select the 3 nodes. So this would be those 3 nodes. Hit apply. This is it. Now, let's try again. Let's delete the global output requests. Let's go down and see if we can find it this way. Because it could easily be that for the first time when I did this, that is the same, that I just did not recognize it. Okay, okay. Form 1 should be phase. So we want phase data. Form 1 here should be phase. Okay, that's set. Now, yeah. So option 1 should go to set ID. And if that's not working, wrong entity. Selection in ID group sets ID pool. I have no idea what this is talking about. But set ID pool. Huh. It's such a strange thing. include 0. Why is that a 0? We'll just leave it like that. Just ignore it for now and see if the model runs through. If it's not working, we will just set it to all and just see about it. But yeah, I think, yeah, something is wrong. Okay. Now, going further, we should also choose the format. Yeah. So additionally, we want to just have a second kind of format to go with our H3D. So for H3D, that's the standard thing, right? But we want to have a second one, so just change that to 2. And the first one, we will just change to opti. So those are ASCII files, which just output displacement values and this kind of stuff into readable by an editor files. So this is pretty neat. So we return here, and now we go into the param card. And now here we will do a bunch of things. So click, yeah. So first off, we will just go to couple mass. So this is a kind of thing which is specific to the direct frequency or the frequency response analysis. So coupled mass, you would want to change that to yes. And I was searching a little bit about that. So you basically have 2 main ways of doing that with the mass in the matrix. So there is this I think lumped and coupled mass approach. And lumped mass I think is a little bit more, no, I think coupled mass is a little bit more precise. One or the other. Here, coupled mass can be more accurate than lumped mass. However, lumped mass is more efficient and is preferred for its computational speed in dynamic analysis. Yeah, so you can read about it here. So this is not in this case the Altair library, but yeah, it's Nastran, so they're pretty similar. And you can, yeah, just see. That may not apply one-to-one here, but on a quick just search, I just find that info here. So I will just use it. So this is just a thing which the tutorial requires you to do. So yeah, I think it's also fair because the model is really small, so I don't think we will have efficiency issues at all. So yeah, we'll just use it like the tutorial suggested. Now, the next thing is a thing about the global damping, which is set to be 0.06. And again, I have to be a little bit careful what I say about this kind of stuff, as I'm not 100% sure what it is exactly, but this is a parameter which controls structural damping. And structural damping is that every structure which is displaced just, yeah, emits a damping force, you could say, or it just has damping characteristics. And this G parameter is used to do this. Now, going into the help, you can see here that you have a critical critical damping ratio, C to C0, and this multiplied by 2 is the G parameter, which you set in here. So it's just a constant you can get. Yeah, but I have actually not a very precise understanding on how you will get it. So yeah, but yeah, you will find out this value and multiply it by 2 and set that as a G parameter. Yeah, I think you would not have to, but for sure it's more realistic if you find that value and put it in there. So just that you be aware that this parameter exists. So structural damping. Then another thing is just at the bottom, which is weight to mass, which allows you, and this is set in to be a factor here, and this allows you to just input all the mass entries in weight units rather than mass units. And also here I have to Google a little bit about this weight to mass factor, and I think I get something here. And here you can see for steel example, you have a density, right? And then you can just use this weight to mass parameter of this one, and this is exactly what the tutorial wants us to do. So this, bear in mind, this has maybe also something to do with units. I'm not 100% sure, because the density should be also applicable in different units. But yeah, so yeah, this weight to mass calculation factor is applied then, and then you have also to input every unit or every mass units in weight units, because once you apply this factor globally, you would have to be congruent in your model. Yeah, so that it's all the same. Cannot do both, right? Okay. Now this is set. I think we are almost done. The only other thing which the tutorial wants us to do is to go for the what is it? The output. Same page. Output keyword, and here you go to the HG frequency. So rather than just outputting the first and last iteration of the for hypergraph data, we want to have it for all iterations. Yeah, that's about it. And I think we can now run the model. Not too happy about this strange set ID thing. I'm really not sure if that runs at all, but let's see. I will just run it as this file here. Permission denied. What? Okay, let's see if I just write a different name. Will there be an error? Or not? Seems like it has completed. I will just launch Hyperview as it is requesting me to do. Okay, just bear with me a moment. Yeah, sorry you did not see that, the last bit, but it was not that interesting, just a file permission thing and me running the job. And all right. Now let's see. I will just quickly jump to the location. So this is here. Yeah, can I open that here as the MVW file directly? Select model reader. That's not really what I want. Let's just open the session file. If I'm open, can I do that? Okay, I have to do this. I would say it should be OptiStruct reader. Nastran OptiStruct. I'm not really sure about this. But if that's not working, we will open the H3D file. Yeah, it's not working. Oh, papa. Just a little bit of a pity. Let's see what the tutorial says. It should, we should open. We should open this in Hypergraph. I'm sorry, not Hyperview, but Hypergraph. Because we're interested in the plots. In the plots of the 3 nodes. Hopefully this will be working. If that's not working, we will go to the backup slides of the tutorial. But let's see. Desktop, Altair temp. Alright, just open it here. Okay. I don't know what I'm doing here. I think we'll just... It doesn't tell me what that is. Unknown index. It's a bit strange, right? It should tell me a little bit more. All right, let's fall back here. Let's fall back here to the slides which we have in the tutorial. So this is what you should expect to get. And I will just in the background launch Hyperview and see what we're getting there. But yeah, so you will see something like this: a displacement and frequency response curve. It's like you have nothing much happening, but around 150 or 100, yeah, something like that, 150 frequency, so I think that's in hertz, you will have a spike. And you have another frequency at 100, 200, 3, 4, 5, 6, 700. So there's another peak. And you have similar things happening for the other nodes as well. So this is more or less that thing. We could also check the displacement file. I think that's fair if we do that. Let me see. Maybe it did not get it right because the set did not work. Yeah, and this would require some post-processing. So this is definitely a thing. Yeah. But you can get some displacement values, and I think in this case, I'm not sure. Could be that it's all nodes here and all iterations. Yeah, I think that's more or less all data. So you could do some cool things here. To be fair, yeah. But that's about it. So as you see, I think what I could cover in this video is how to set it up. This is a Hyperview here. Let me see if you can just maybe plot any contour here. So you have displacement, and then what do you do with it? You have frequency. Yeah, at your different frequency points, you could for sure get your how do I choose the load step here? So this is more or less how it works. And here you could also go to this, I think, and then you have the different frequencies, right? Hopefully. Yeah, you see this F value here? This is increasing when you just go. I'm sure there's a better way to do it, but just because I'm not really knowing what I'm doing here. So this would be different kind of frequency responses you would get for different frequency excitations. That's pretty cool. And you can also see how if you change the frequency, you can see how the shape is shifting. That's not, it was not here, but here you can see that. Yeah, sorry. This is me being a little bit nerdy about it because I want to just go a little bit more into this topic and explore it. But yeah, I think what I could achieve in this video is just to cover the basics of how to set it up. This direct response frequency response analysis for first tutorial. I'm definitely looking to go much further into this topic in future tutorials. So just that you see what we could do as a next thing. So we are here in the OptiStruct tutorials, and this is advanced small displacement finite element analysis, and we were here at the first thing. So obviously, a modal frequency response analysis of the plate should be next to just see how the different approaches look like and how to apply one of the two. And then we also had the random response of a flat plate we could do. So this would be another thing. And now let's see how it goes into the future. And also, yeah, let me know what you think about it. Should I go into a different topic more? Is that what you wanted to see? Is there some questions we should research and get the things sorted out? Do you have the same experience with setting up the set and then you have that error with the output request and stuff like that? So just let me know how it is best for you. And in the meantime, thank you for being here, for watching, and if you like the video, please for sure like and subscribe, and I see you in the next video. Bye guys.